All right, so in this video, what we're going to be talking about is something that is known as partial fractions. Now, partial fractions, what a partial fraction is it's a technique that you should have actually learned if you were to take Math 1050, where we can make something that is complicated as far as a fraction go become much simpler. And you'll see what I'm talking about in just a second. But in order to understand why we're going to learn this method, if you remember when we were trying to take the antiderivative of any of these three things, like especially this second one here where we had 1 over x, we knew that the antiderivative of that is the ln of the absolute value of x plus c. Or if we had one that was slightly more complicated, like this one, it's not way more complicated, but the antiderivative of 1 over x plus 1 would be the ln of x plus 1 plus c. And remember, we can do this simply by knowing if this function is linear down on the bottom of the fraction. We can just make it ln, and then technically out front, we're multiplying by 1 over the derivative of that. It even extends if there is a number on the top. Like what I could do here is I could move that 4 out in front. Then I could have 1 over x minus 2. Then I would take the antiderivative of that, and I would just have 4 times the ln of the absolute value of x minus 2 plus c. Like all of those are antiderivatives, and they're very easy to take the antiderivative of. It's the only type of fraction that we have that we can actually take the antiderivative of very, very quickly. Every other fraction either involves u substitution or some other method that is just more complicated than any of these right here. So what our goal is going to be, at least in this particular lesson, is how to take a fraction that doesn't look like one of those right now. Like this fraction right here, you'll notice I've got 1 over, then I've got x times x plus 1. Well, in order to do this problem, u substitution would not work if I was to do this problem. And nothing else would work actually in order to take, if I wanted to take the antiderivative. And so what we're going to do is, if you think about this for just a second, once upon a time, it could have been that this was two separate fractions. One of those fractions had x on the bottom, and the other one had x plus 1 on the bottom. And those two fractions were either adding together or subtracting. So we'll just assume for a second that they were adding. And there was a different number on the top of both of them. Okay? Now, the issue is, and I wish it was easy, but when I look at these problems, the issue that I have is I don't know what number was on the top of these fractions. Because if I did, I could take the antiderivative really easily, and then I would know what the antiderivative of this particular thing is. So what we're learning now, and I won't be referencing calculus anymore for the rest of this video, is a technique that we can use to find out what number is on the top of each of these different fractions so that I can take the antiderivative of it. In order to do that, what we do is we give each of these different numbers that I don't know right now a variable. Now, by and large, when these problems are shown, when you use the partial fractions method, the letter that we use every single time, the letters that we use are A and B, okay? So what we do now that we know that both of those letters are up there is we actually try and find out, like we carry out what we would normally do if I were to find a common denominator, remembering the entire time that this will be equal to this in the end. So I'm going to find a common denominator between these two. I'm going to multiply the first fraction, top and bottom, by x plus 1. I'm going to multiply the second fraction by just x, top and bottom. If I were to do that, I would see that I've got a times x plus 1 on the first fraction, plus b times x on the second fraction. And if you think about it, what we have here, if we get a common denominator of x plus 1 times x, is I will have x times x plus 1 on the bottom of my fraction. If you think about this a little bit more, these two things are equal to each other. Remember, we're saying the entire time that these two things will be equivalent. Well, now they have the same denominator. So I don't have to worry about the denominator anymore. Instead, I could say that 1 is equal to a times x plus 1 plus b times x. What we do next, these next couple steps are not entirely intuitive the first time you do the problem, so I'm going to walk you through them to make sure you understand what's going on. I am going to multiply this a into both of these terms. Okay, so I've got ax plus a plus bx is equal to 1. What we do now is any term that has an x in it, we group those terms together. So I'm going to put them by each other. So ax plus bx plus a. And then I notice in these first two terms, both of them have an x. So I'm going to factor an x out of each of those two terms. So I'm going to have a plus b, and those two things multiplied together, or added together, multiplying by x, that would be the same thing. So I've got a plus b times x plus a, and that is still equal to 1. Now, that step didn't make an awful lot of sense, why you would do that. And this next step also doesn't make a ton of sense initially until you're like, okay, I can see why you would do that. Over on the left-hand side, I've got 1, but technically, if I wanted to, I could write this as 0x plus 1. Now, the reason why we would do that is in this case, if this side and this side are going to be equivalent to each other, because they need to be, we were saying that we're not losing equivalence throughout the entire problem, that in order for that to be true, a plus b would have to equal 0. So I'd have to say a plus b is equal to 0. At the same time, you'll notice I'm adding a constant number onto the end, and everything that's left over on the right-hand side is just a. So I could also say at the same time that, in order for this to be, true, that a would also have to equal 1. Well, what we have here, and this will make a little bit more sense on the next example because this one's a little bit easy, I can see that a equals 1. What we have just discovered is over here, when I was trying to separate these two variables, the number on top, and I'm not sure why it keeps doing that, okay, the number on top here, that where the a is going to be, that number is going to be a 1. So I know that I've got 1 over x plus whatever b is going to be. And if I can figure out what that is, then again, we would be able to take the antiderivative. Well, if a equals 1, then a plus b at the same time must also equal 0. So I would have 1 plus b, that must equal 0. So b, if I were to solve for it, I would get negative 1. So I would have negative 1 over x plus 1 because I just found out what my b was. This method that we have used is what is known as using partial fractions, where we take something that is complicated and we break it down into where it came from as far as having different denominators. Once I get it to that point, this would be really easy to take the antiderivative of. So that's how we do that particular problem. Now I do want to do another couple of examples, make sure we got this down. This one's slightly more complicated. Not way more complicated, but slightly more. Notice in this problem, I've got x minus 5 on the bottom, and I've got x plus 4 on the bottom. And I want to know, if those were two separate fractions once upon a time, where those numbers, what numbers were on top of those. So I've got a and b. Just like before, what we do is we get ourselves a common denominator. So I'm going to multiply the first fraction by x plus 4. I'm going to multiply the second fraction by x minus 5, top and bottom. So what I have here is I've got this fraction 3x minus 10 over x minus 5 times x plus 4. That's going to be equal to, I'm going to distribute the a into both of those terms. So I'm going to get ax plus 4a. Then I'm going to distribute the b into both of these terms. So I'm going to get plus bx minus 5b. And all of that is over x minus 5 times x plus 4. Well, now again, those two fractions are equivalent to each other, so I don't need to worry about the denominator anymore. Instead, what I have is 3x minus 10 is equal to, again, what we do here is group everything that has an x in it together, and everything else that does not, we just leave on the outside. So I've got ax plus bx plus 4a minus 5b. So now what we do is we say, okay, now that I've got that, what I want to do next is I want to factor that x out of those first two terms. So I get a plus b times x plus 4a minus 5b. And that is going to be equivalent to 3x minus 10. Well, just like we had before, I've got something multiplying x, and I know that something has to equal 3. So I'm going to have a plus b is equal to 3. This one's a little bit different because you'll notice I've got everything else left over, 4a minus 5b. In order for these two things to be equivalent, that has to be equal to negative 10. So I've got 4a minus 5b is equal to negative 10. Well, this right here is a system of equations. And back a long time ago, probably in Math 1, you learned how to deal with the system of equations. One of the ways that you learned how to deal with it was by using substitution. So I'm going to choose one letter to get all by itself. And it doesn't matter which letter or in which equation. I generally like to go with the easiest one to get by itself. So I'm going to get a all by itself in the first equation. So I'm going to get a is equal to 3 minus b. And I've also, again, once I know that, I'm going to take that and substitute it in for that a right there. So I'm going to have 4 times 3 minus b minus 5b is equal to negative 10. Then we're just going to solve this thing. So 4 times 3, I'm going to distribute that in. That's 12. This one right here is negative 4. So I get negative 4b minus 5b. So what I have now is 12 minus 9b is equal to negative 10. So I'm going to minus the 12 over, so I get negative 9b is equal to negative 22. Divide both sides by negative 9. And I get that b is equal to 22/9. Now I know that number doesn't look great, but there's nothing wrong with getting a fraction. That means the number on top for b is 22 over 9 over... it's just x plus 4, which looks bad, but we can still deal with it. We'll talk about that in the next lesson. Now that I know what b is, I can just take that b and plug it back into that equation, and I would find that a is equal to 3 minus 22 over 9. I know that's a little bit difficult to try and visualize. You might have to use your calculator to find that, but that turns out to be 5/9. So a in this case is equal to 5/9, so I get 5/9 over x minus 5. Now what I've done is I've taken this, which was a fraction that I did not know how to take the antiderivative of, and I've changed it, although it doesn't look great, into two separate fractions that I would be able to take the antiderivative of each of them fairly easily. So again, I know there's an awful lot going on here, and I know this method seems fairly complicated, but hopefully that makes sense on what we do to take a complicated fraction and change it into something easier. On this one, actually, we're not going to worry about that, so we won't worry about those right now. So hopefully that made sense. If you have any questions about this one, please let me know.